Today's lecture is on energy and mineral resources. So we use many resources that we get from the earth. These include resources that can be used for energy and also mineral resources that we use in construction or making products. So construction might be the rocks that are used to make a curb, like a granite curb, or part of the facade of a building or countertops. Minerals that go into making products might be clay minerals that are used in ceramics, or gypsum that is used in gypboard, like drywall. So we have renewable and non-renewable resources. Resources that we generally expect will not run out are considered renewable. So wind energy, we do not expect to run out of wind energy. We don't expect to run out of running water, and gravity is driving the running water, like a stream, right? We don't expect solar energy to run out, and we don't expect geothermal energy to run out. So these are all examples of renewable resources. Resources that are present on Earth in a finite amount that are gone once we consume the reserve are considered to be non-renewable. So we have oil, natural gas, coal, minerals, and metals. Now we are able to recycle some metals and other materials, but they are still considered to be non-renewable. So where does energy come from initially? We have solar energy, gravity and running water that's not gravity driven, fossil fuels, inorganic chemical reactions, nuclear fission, and geothermal energy, which is the energy from the Earth's interior. So then I'll go through all of these. So we start with solar energy. The sun provides light and heat, and photons from the sun can be used in photovoltaic electricity generation, and that's with solar panels. And solar energy drives the weather patterns on Earth, which then can lead to wind, and then we're able to use wind energy. So wind energy is driven by solar energy. And the sun also allows for photosynthesis. So plants and algae use sunlight. They have the process of photosynthesis, and then that leads to plant growth and the growth of algae. And then other organisms consume those plants or algae, if we're talking about algae. And then we have an energy transfer up the food chain in the form of food. And that's called biomass. So biomass is wood or other plant materials. No, the food is not called biomass, sorry. It's related to biomass because not only are we able to transfer energy up the food chain, starting with the photosynthetic organisms, but we also then we have the creation of biomass, which is the plant materials, the wood. And that can also be used as a fuel. but that originally is coming from solar energy. So everything on this slide is initially driven by solar energy. And we have gravity and running water. So we have potential energy is stored in rivers that flow downstream. And then we can actually harness that energy as the river water flows downstream. You can harness that as hydroelectric power. Now, in this case, you could also reroute water so that it starts at a higher point and then it goes through this water wheel. And then the spinning of the wheel will generate electricity. So that's hydroelectric power. Also, you can build a high dam and then you're also spinning a turbine which generates electricity. So in this case, this is a dam where the water is going through the dam and then the hydroelectric power is generated. Now this is other energy resources related to running water that's not gravity driven. So we have tides and waves. So you can put these turbines in an area where the water is flowing due to waves or tides. For example, a tidal channel like the East River in New York City. And a tidal channel has water flowing either in or out of the channel, during high tide or low tide. So that tidal current could spin the turbine and produce electricity. And you could also do this in an area where it's a lot of waves. And then we have fossil fuels, oil, natural gas, and coal. Natural gas contains methane. So we could think of fossil fuels as stored solar energy because millions of years ago, plant and algae material was buried and then led to the formation of fossil fuels. So initially that plant material and the algae formed as a result of solar energy related to photosynthesis. So it's indirectly solar energy, but it's stored as this bioorganic material. So that's what fossil fuels are. Then we have inorganic chemical reactions. So chemicals like dynamite or hydrogen, which would be used in a hydrogen fuel cell, can create energy from chemical reactions. And then also nuclear fission. So radioactive atoms can split into smaller pieces in a process called nuclear fission. And then tiny amounts of mass transform into a large amount of energy during the process of fission. So this could create a lot of energy. And this is called nuclear energy. And this is an image of a nuclear power plant. This is from The Simpsons. Then we have geothermal energy. This is energy that comes from the Earth's interior. So inside the Earth is hot. And that heat is a remnant of the Earth's formation, as well as being generated from the radioactive decay of isotopes. So we have a steady temperature, depending on the depth that, underground, there's a steady temperature called the geothermal gradient. Again, it's depending on what depth you're at. And we could actually harness that energy from from the earth. So as you can see, there's a lot of different energy sources. Much of the electricity in this country, in the US, is generated from coal burning power plants. And the burning of fossil fuels like coal is not 100% clean. And it also releases greenhouse gases into the atmosphere. So the US, using a lot of coal burning power plants to create electricity, we might want to change over time to using cleaner energy that does not release greenhouse gases in the amounts that we have now. First, we will focus on fossil fuels, which we call hydrocarbons. And we will talk about coal, oil, and gas, which are fossil fuels. And we will also talk about other energy sources in more detail, and then we will discuss mineral resources. So hydrocarbons are molecules that contain only carbon and hydrogen atoms. And hydrocarbons include natural gas and oil. And they yield a great deal of energy per unit of volume, meaning a small amount of volume will give you a lot of energy. So we call these energy dense. Oil and gas mainly derived from organic matter from plankton. Plankton are tiny floating organisms. Plankton can include algae, protists, and microscopic animals. When the plankton die, they fall to the seafloor or the lake floor, depending on where they're living. If the environment does not have a lot of oxygen, then the plankton will not decay. Instead, they will just be buried within the sediment layers. And that lack of decay is important for the formation of fossil fuels, because over time, that organic rich sediment gets buried under more sediments and becomes lithified and turns into a rock. And we call that a black organic shale, which is a source for hydrocarbons later on or in the present day. Okay, so these plankton were deposited millions of years ago, and then we're using the hydrocarbons today that formed from those plankton millions of years ago. Okay, and the fact that it's not rich in oxygen and it has very little oxygen allows for the burial of organic material in abundance. Otherwise, it would be broken down by bacteria, for example. Okay, so here you have the plankton die and fall to the bottom. And then you get more sediment deposited on top. And then here is that layer getting compressed. Okay, so this layer here is now down here underneath all this sediment. And now it's getting warmer. It's now 15 degrees Celsius down here because as you go deeper into the earth, it gets warmer. And then at about 80 degrees Celsius, the sediment is transformed into that black organic shale. And then we start to form something called kerogen under more heat and pressure. Okay, so as the heat and pressure continue, we form kerogen. And then as the temperature increases further, as you get more burial deeper down underground, the kerogen turns into oil. And then the oil starts to rise up through cracks in the rock, and then you could go ahead and extract that and use that as oil, basically. Okay, now that kerogen that I mentioned is a waxy material, and shale rock with more than 25 to 75% kerogen is called oil shale. This is what an oil shale looks like. You can see like the side of it is cracked off. You can see the inside, it's pretty dark. It's rich in organic material, including kerogen. And then if that oil shale is buried even deeper, again, the kerogen will start to turn into oil, and that's called hydrocarbon generation. So the kerogen breaks down into natural gas and oil. This process only occurs between 90 degrees and 150 degrees Celsius. Okay, so you see the kerogen turning into oil in this diagram is 120 degrees Celsius, right? So that's in between 90 and 150. So there's that zone of temperature underground where hydrocarbons are generated. And again, that's the breakdown of kerogen into gas and oil. And then oil and gas companies look for reservoir rocks that they can extract oil and gas from. So reservoir rocks are rocks that can be drilled into that have a high porosity and a high permeability. So that goes back to what we talked about in the groundwater lecture. So for example, poorly cemented sandstone has a porosity of about 35%. So that would make a good reservoir rock. And again, reservoir rocks, it's when you have the oil that starts rising up out of the oil shale. It starts rising up, and eventually in some locations, it'll start collecting within a reservoir rock. Okay, so the source rock is that rock down here. Okay, that's the source rock. And then the reservoir rock is where the oil and gas collect. Okay, so in this diagram here, you have this source rock here. And then the oil and the gas start migrating upward. And in this case, they're collecting right here. Okay, so this would be the reservoir rock. So then it would be cost effective if you were to put a well here and then pump out this oil. This would be a cost effective location to pump the oil out of because it's trapped by this rock above. So you get like this pool of oil underground. So conventional reserves of hydrocarbons allow for drilling into reservoir rocks and pumping out the hydrocarbons. Okay, so we call that conventional reserves. Okay, conventional reserves, you find a reservoir rock that has an accumulation of oil or gas, you put in a well and you pump it out. Okay, we call that a conventional reserve. This is what it looks like, right? You have this oil well and here's a pump, and this stores the oil or the gas that is extracted. And this shows you regions of major known oil reserves. Oil reserves are found by geologists. The geologists use different techniques to look for the reservoir rocks and look for those pools of oil underground. So they were found by geologists. One of the settings that oil reserves are found in is sedimentary basins along passive continental margins. So an example of a passive continental margin with a sedimentary basin with oil reserves is the Gulf of Mexico. Okay, we have a large reserve of oil just offshore in the Gulf of Mexico. Also in Texas, you have quite a lot of oil reserves historically. The largest reserves on Earth are associated with countries around the Persian Gulf. So 60% of the world's reserves are around the Persian Gulf. So why is there so much oil in the Middle East? During the Jurassic, 135 million years ago, through the late Cretaceous, which is 66 million years ago, the Middle East region was situated between 20 degrees north and 20 degrees south of the equator. So this resulted in a tropical climate. So the Middle East was tropical, and that led to a lot of productivity of plants and other synthetic organisms. And then the sediments deposited during that time period were rich in organic matter and then were subsequently buried by porous sandstones. So the paleoclimate and the geologic history of the Middle East is what led to the large reserves of hydrocarbons there. So it's just the unique geology of the area. So then we have something called unconventional reserves of hydrocarbons. So unlike the conventional reserves, unconventional reserves use rocks or sediments that contain hydrocarbons. They can't just be drilled into and pumped out. Like pumping out the hydrocarbons is not necessarily something that you could just do. For example, if the oil is too viscous to pump out, or if the rocks are not permeable or impermeable and won't allow for the flow of oil or gas, then you can't just simply drill into and pump out the hydrocarbons. So unconventional reserves include shale oil, shale gas, tar sands, and oil shale. And then I'll explain. So here's shale oil and shale gas. So here is a conventional well where you would just dig downward and then pump it out. But in the case of unconventional reserves, we need to use directional wells. So in a directional well, you dig downward and then you dig up, you have the well going along inside the shale layers. And then that allows for more collection of oil. Okay, so this is a well. You install the well through the shale layers, allowing for the collection of gas and oil. And this is a map of North America showing you the unconventional fields. So the pink color is the current areas where they are collecting hydrocarbons from. And then the purple is prospective areas. So then we have tar sand. By the way, I'm not saying Tarzan, I'm saying tar sands. So tar sand is a source of heavy oil. Heavy oil is a mixture of clay, sand, water, and bitumen, which is a combustible organic material. It's thick and sticky, it's tar-like, it's a heavy oil with a high sulfur content. So northeast Alberta in Canada has 3/4 of the world's tar sands resources in sandy soil, but it's beneath a vast area of forest. So you have the problem of deforestation there as well. So this shows you tar sands mining in Alberta. And this is the sand with the hydrocarbon in it. And we have oil shale. Oil shale is rock that contains a solid combustible mixture of hydrocarbons called kerogen, which we talked about earlier. And then you can process the rock and produce shale oil, or otherwise known as heavy oil. So here is your oil shale, and it has high amounts of kerogen. And then you process the kerogen out and you can extract oil from it. So these are just different ways of getting hydrocarbons other than just drilling into the ground and pumping it out. Then we have hydrofracturing or hydrofracking. And that's when water is mixed with sand and toxic chemicals that are pumped underground. And then explosives and high pressure are used to fracture the rocks deep underground in order to free up natural gas that's stored down there. And then the gas flows out along with a toxic slurry of water, salts, and sometimes even toxic heavy metals that are pulled from rocks underground. And then you're able to collect the gas. Okay, so you fracture the rocks underground, and that allows for a release of the gas that's underneath in the rocks. And then you're able to extract the gases. But also, the process could potentially contaminate groundwater in the local area as well. I've seen photos of people near fracking areas. Fracking is what you call it, what you could also call it. So there are photos of people who turn on their faucet, and then if you light a match next to the faucet, it actually burns. Also, I've seen reports that fracking could potentially lead to very small earthquakes. And then you do have the risk of groundwater contamination with other chemicals that are the fracking chemicals. This is just another picture showing you what's going on. So they inject water and chemicals, you fracture the rocks down here, and then the gas flows from the cracks into the well, and then you're able to extract the gas along with that water and whatever chemicals you injected down there. Then we have coal, which is another fossil fuel. Coal is a black, brittle, carbon-rich sedimentary rock made up of the altered remains of plants that grew in swamps millions of years ago. Okay, so this is an artist rendition of a coal swamp. This is most likely from the Carboniferous period, millions of years ago. This is a pile of coal. So coal forms from large quantities of undecomposed dead plant material that accumulates. And that's because the dead plants don't decompose because they're deposited in a swamp, which does not have a lot of oxygen. So the plant matter is not decomposed, and then it is buried in the sediments underground. And then that forms a layer of peat. So peat looks like plant remains, but it's the starting point of coal. The next step is that the peat gets compacted as it gets buried under more layers, and it starts to alter into something called lignite. And then further burial, more pressure, and some heat from being buried underground is going to form bituminous coal. Now, we do also have a metamorphic coal, which is called anthracite. This shows you the locations of the world coal reserves. The black is anthracite and bituminous coal. And the brownish red color is lignite. And it shows you a pie chart by region. So we have a lot of coal reserves in Asia Pacific area, Europe and Eurasia, and North America. Those are where most of our coal reserves are. And that makes sense as to why we use coal burning power plants in the US. It's because we have coal. It's readily, it's pretty available. Coal is also very cheap. Okay, and this shows you again the progression of the peat. And then it's buried deeper and it becomes lignite, and then buried even deeper and it becomes bituminous. And notice it gets more compacted together. And then eventually you have these layers of coal. So it's pretty easy to extract because it's in a layer. It's just sitting right there in a layer in this photo. In other cases, you have to go underground though, and have an underground mine for coal. So this shows you an example of mining at the surface. So the method of mining that you're going to use depends on how deep the coal seam is. And we call it a seam, okay? So it's basically a layer of coal. So in this diagram, the coal seam is not that deep. So they were able to just remove the upper layers of rock in this section right here, and then you just go ahead and extract that coal. Okay, but you just need to remove these top layers of rock. So this is called strip mining. Strip mining is done if the coal is less than 100 meters deep. Okay, then it's economically feasible to just do strip mining. If the coal is deeper, then you're going to need to do underground mining. This is an old abandoned strip mine called Bear Valley Strip Mine. This is in Cole Township in Pennsylvania. So they cut down all of the rocks above, removed the coal, and you're left with this rock that used to have, it used to have layers on top. And this is kind of like a cliff now. It goes all the way down. This is just a picture of some underground mining for coal. Underground mining, though, is not that safe in some cases, and it's dirty, and the people who are mining are breathing in the coal dust. And there could be fires or explosions. You can have cave-ins of the roof of the mine. So it's not the safest thing to do. Oops. Then we have geothermal energy in terms of electricity generation. And then I'm going to talk about heating and cooling of a home using geothermal energy. So geothermal energy can be used for both of those. Okay, heating a home, cooling a home, or generating electricity. So one form of harvesting geothermal energy is at a geothermal power plant near volcanic areas. So for example, in Iceland, which is on the Mid-Atlantic Ridge, you have a permanent magma activity underground. So you have heat closer to the surface because of the magmatic activity. So what you're able to do is use steam from heated groundwater, and then that steam is harvested and used to turn a turbine. And then once you turn a turbine, you're able to create electricity or generate electricity. So basically, electricity generation, you just need to spin a turbine. So all of the different ways of spinning a turbine, you can do that with hydroelectric power at a dam. You could do that, in this case, using steam, wind energy, okay? Something like solar energy with solar power, the photovoltaic cells, that does not use a turbine. Okay, but other forms of generating electricity do. And the geothermal energy this is renewable because, especially in Iceland, where you're on the Mid-Atlantic Ridge, you're going to have the magma activity pretty much all the time. So you're going to have that steam generated from heating the groundwater. And then you're producing less fossil fuels emitted into the atmosphere. This is just a schematic showing you the geothermal power plant. Okay, the hot groundwater, the steam is collected and then used to spin the turbine, which generates electricity. Then we have the geothermal energy that's used for cooling and heating homes. So this is a little bit different. This is something that it's not a widespread way of cooling or heating homes. It's more common in the US for people to use oil or natural gas to heat their homes. But what this is you set up a system in the house and then you pump into pipes that are underground. Okay, the pipes are buried underground, and there is a liquid. I think it's something similar to like an antifreeze, where it is sensitive to temperature changes. So you send the liquid out into the pipes, and in the summertime, the liquid is holding heat collected from inside the home. And then you're sending the heat outward, and then the ground is able to absorb that heat. And in the winter, you have a cold liquid flowing through the pipes, collects heat from underground, and then brings that heat back into the home. And then the heating and cooling system works to either cool the house or heat the house, depending on the season. So it's pretty interesting how this works. And this does not emit fossil fuels. You're only using the heat from underground. Okay, and this is just another schematic. So it shows you the cooling and the heating. It's the same system though. So you have cooling, you're dispersing the heat from the home back into the ground, and then the ground absorbs that heat. Or you are taking heat from the ground and bringing it into the home to heat the home in the winter. So then we have mineral resources, metals and non-metals. So metals include gold, copper, lead, iron, and aluminum, just as examples. And then non-metals, we have sand and gravel, gypsum, halite, which is rock salt, and limestone as examples. So first we'll talk about mineral resources that are metals. So we have native metals versus ores. So native metals are a pure form of the metal, and ores are minerals that metals can be extracted from. So native metals, you would find gold, copper, silver, iron in its natural pure form. So here is a rock that has gold in it. You would just take out that gold and use it to make jewelry or whatever else you're going to use the gold for. So what is an ore? An ore is a mineral that contains a large enough concentration of a particular metal to make it profitable for extracting that metal. For example, aluminum is mainly derived from the mineral bauxite. And this is what bauxite looks like. And the penny is just used as a scale. So you can see, you can get like a better feel for how large the rock is. And this is an example of a copper ore called chalcopyrite. So how do ores form? They form through magmatic deposits, hydrothermal deposits, sedimentary deposits, and residual mineral deposits. So first we'll go over magmatic deposits. So when igneous intrusions of magma cool and solidify, minerals called sulfide ores can form. So sulfides are minerals that contain a metal combined with sulfur, such as galena, which is lead and sulfur. So we call it a lead sulfide. Hydrothermal deposits are where groundwater can heat up as it passes through and around igneous intrusions. The hot water becomes a watery solution as it dissolves metal ions. And then the metal ions can then bond with other elements and precipitate out into fractures and pores in the rocks that are underground. And this forms hydrothermal deposits of minerals. Okay, so here's a representation of the groundwater that is hot because it's near the magma. It dissolves, it collects dissolved metal ions from rocks and the magma, and then those could precipitate out into fractures in the rock. Hydrothermal deposits can also form around black smokers, which are hydrothermal vents at mid-ocean ridges. And this forms in a similar way. So you have ocean water passing into cracks in the hot basalt. And then the water collects dissolved ions and then spews back out of this vent, precipitating out minerals. So you get these sulfide minerals. Then we have sedimentary deposits. So sedimentary layers such as banded iron formations that formed 2.5 to 1.8 billion years ago are a source of iron. These are related to the oxygenation event when you had the cyanobacteria creating a lot of oxygen in the atmosphere through photosynthesis. And then the great increase in oxygen in the atmosphere led to a lot of oxidation. So that oxidation related to sedimentary layers of iron oxides, that's all a good source of iron today. We can go back and extract the iron from this. Then we have residual mineral deposits. So soils in tropical climate zones experience high amounts of leaching. That's when rainwater removes soluble elements from the upper layers of the soil, leaving other elements behind. These types of soils may develop high concentrations of iron oxide and aluminum oxide, resulting in the soil itself being an ore for iron or aluminum. For example, that bauxite that I mentioned, that could form as a residual mineral deposit. So this goes back to the soil lecture where I showed you a picture of a laterite, and the laterite was very thick, reddish orange soil, tropical soil. So that would be an example of a residual mineral deposit where the soil itself is a source of iron or aluminum. So as you're seeing, a lot of this lecture relates back to previous topics that we've already talked about, like the geologic history, sedimentary, groundwater, soils, igneous rocks. Then we have the mineral resources that are non-metals. So here are some examples. You have sand. Sand is mostly silicon dioxide or quartz. It's used in the production of glass, bricks, and concrete. Then we have limestone, which is calcium carbonate or calcite. And if you crush limestone, it can be used to make concrete and cement. Limestone is also used in the production of lime. Lime is calcium oxide or calcium hydroxide, and you use that in different industries. So this is lime, not this kind of lime, okay? Not like the citrus fruit. It's lime as in limestone. And if you ever do any gardening or you treat your lawn, if you have a lawn, some people will put lime. It's like a white powder. You put lime down and that changes the acidity of the soil. So if the soil is too acidic, you put lime on it and it makes it less acidic. That's one example for lime, how lime is used. Okay, so concrete and mortar are both made from a slurry of aggregates of sand and or gravel mixed with water and cement. And then you let the slurry set, dry, and harden. Cement is a powder that's made of lime, quartz, aluminum oxide, and iron oxide. Most cement used today is called Portland cement, which contains specific proportions of limestone, sandstone, and shale. And then it's heated in a kiln and then made into a powder. So you can see all of these different materials that are earth materials that are resources. And we have other non-metallic mineral resources and some of their products. Gypsum is used to make drywall. Clay minerals can be used to make bricks, ceramics, and kitty litter. Sulfur is used to make fireworks, gunpowder, or matches. Halite is table salt, right? You cook with halite, basically. And then you also have quarries where you have a removal of large slabs of bedrock. And then that's used in construction or for countertops or curbs. So here is someone measuring out a slab possibly to use for a countertop. So that brings us to the end of the energy and mineral resources lecture.